Hello everyone, and welcome to my ProSeminar experimental physics presentation. The topic of this presentation is the Nobel Prize in Chemistry in 2011. The Nobel Prize was given for the discovery of quasicrystals. So I will start with a quick overview. First I will introduce Daniel Shechtman, the Nobel Prize laureate. We'll discuss some background concepts to help you understand quasicrystals. I will speak about the experiment. I will show how we can generate quasicrystals and how we can understand them a bit better. And I will finish with some properties and the application. Daniel Shechtman, the Nobel Prize laureate, was born in Tel Aviv in 1941. He studied his bachelor, master's, and PhD in the Technion University in northern Israel. Over there, he also did the research throughout most of his career. In 1999, he already won the Wolf Prize in Physics for the experimental discovery of quasicrystals, non-periodic solids. I mentioned this because the Wolf Prize in Physics is considered often as the second most important prize in the scientific, in the physics world, and it is also quite a good indicator for future Nobel Prize laureates, since roughly 1/3 of the Wolf Prize winners end up winning later also the Nobel Prize. In 1982, when he did the 1982, when he did the discovery, he was working. He was doing research. He was on a sabbatical from the Technion University, and he was doing research in the National Institute of Standards and Technology in Maryland, in the United States. At which time he was affiliated to the Johns Hopkins University. His research was focused on applicative materials for the aerospace industry. So I will start with a few background concepts in order to help you understand the quasicrystals. So I will start with the crystals, then I will discuss about symmetries, about tilings, specifically Penrose tilings, and later on crystal twinning. A crystal is defined as a combination of a lattice and a basis. So a lattice is a set of mathematical points in space, which every point represents a point where the surrounding is identical, meaning if we stand here or here, we cannot tell the difference. In this example, we have a two-dimensional plane or a two-dimensional lattice. And if we were asked to continue draw the points to the right, we would know exactly how to continue drawing them. This is of course due to the periodicity that we have here. As I said, this example is two-dimensional, but if we would take just one of the rows and we were asked to draw the next point, we would know also exactly how to do it in basically a line, which is a one-dimensional plane, or if we would have to do it in a three-dimensional plane space, then we would just draw the points basically out of the plane of the screen. To each lattice point, we attach a basis, which is a physical object. It could be 1, 2, 3 atoms, or even a whole molecule. Another way in which a crystal was defined is a solid composed of atoms arranged in a pattern periodic in 3 dimensions. This was an old definition, and indeed actually X-ray crystallography was born in 1912 by von Laue, and we had a presentation about this already actually. And until Shechtman's discovery in 1982, this branch in physics and chemistry was already 70 years old, and as a result we can see that an old definition was actually quite strict and unequivocal. But I must emphasize that this is not anymore a definition, but It is here to demonstrate all the definition and the impact that the discovery of quasicrystals had on this field. And the next concept is of rotational symmetries. Rotational symmetries are operations which can be applied on objects, and after applying those operations, we get the same object. For example, we can rotate an object by 180 degrees, and we get exactly the same object. This is called a twofold rotational symmetry. We can also have a threefold, fourfold, and etc. In crystallography, it was typically thought that there are four possible rotational symmetries, namely the 2, 3, 4, and 6-fold rotational symmetries. And this also connects to tiling. So tiling is a way to fill up space. In this case, the plane in the two-dimensional example. Here we have triangles, squares, and hexagonals. So we have objects that have 3, 4, and 6-fold symmetrical rotational symmetries. And we can see that this way we can really, as said, fill the space, and we can also fill it in periodic patterns as well. So we would know how to continue here this lattice, and also here and over there. On the other hand, tiling of objects that have 5-fold rotational symmetries as a pentagon or 7-fold and above is basically impossible in that sense, that we would always get either gaps or overlaps. Therefore, an example like you see here was considered to be an example, or the argument that in classical in crystals, basically a 5-fold or 7-fold and above rotational symmetries are not allowed. They're called forbidden. Basically, mathematicians ask themselves for many years, how can we fill a space, a plane, in a aperiodic pattern? And already in the 1960s, an American mathematician managed to fill a plane with the help of 20,000 different tiles, and he got aperiodicity. Since 20,000 tiles are quite a lot, this was not that satisfactory, and the mathematicians continued on investigating, and they managed in the 1970s, a mathematician and physicist named Sir Roger Penrose came up with only 2 tiles to fill up a plane in or also 3D in aperiodic patterns. We can see here in these images also the floor upon which he stands. The tilings are 2 rhombi, named of course the Penrose tilings. The 2 rhombi are of fat and thin rhombi of 72 and 36 degrees. They do not go together arbitrarily, but they must follow the matching rules, meaning only edges that have the same amount of arrows must be connected, and connected in such a way that they point towards the same vertex. It is also important to note that the ratio in the Penrose tiling, the ratio between the number of the fat and the thin rhombi is equal to tau, the golden ratio, which is an irrational number, and it is also the limit of the Fibonacci sequence. So the Fibonacci sequence, a quick recall, is a sequence with the summation of the last 2 elements in the sequence, with the first 2 elements being 0 and 1. So the connection of Penrose tilings and the crystallography is quite interesting, and in 1982 a British crystallographer, Alan Mackay, published a very interesting paper which laid some theoretical foundations to Shechtman's later discovery. In his work, he took the Penrose tiling and he basically decorated them with the virtual atoms with the circle shapes on the vertices of the tiles. He took this image and he used it as a diffraction grating. So he basically wanted to see what will receive, what kind of diffraction it would receive basically in the reciprocal space. And he actually got a very interesting image. He got basically an image that locally in the center it looks as a tenfold symmetry, but actually with some further investigation it's actually a diffraction of a 5 that shows a 5-fold symmetry. So this was the first connection between aperiodicity and forbidden symmetries. So the fourth concept is of crystal twinning. Two crystals of the same kind that have grown together in a certain symmetrical manner is the definition. And the idea is that it's important to note that the allowed symmetries of 2, 3, 4, and 6-fold that I mentioned before are only allowed for single crystals, meaning often when basically when forbidden symmetries are observed in a diffraction pattern, it's usually because of crystal twinning, that basically we see the superimposition of multiple crystals, and this results in an image that gives forbidden symmetries. So it's basically a wrong way to characterize a material. So as I said before, in 1982, in the National Institutes of Standards of Technology in Maryland, Professor Shechtman was doing his research, and as he also mentioned in his Nobel lectures, the transmission electron microscopy played a very central role in the discovery of quasicrystals. And since the first quasicrystals were actually very small grains and very thin, and it was essentially essentially to detect them and study them basically with the help of TEM. So the idea of the transmission electron microscopy is to use a beam of electrons instead of light. This technique is basically based on the wave-particle duality of the electrons, and the microscope consists emission source, electromagnetic lenses, and a detector. As I said, it is very useful for thin samples, and the electron beam is accelerated and focused by the lenses, such that the beam here transmits through the sample and resulting in an image on a detector that is usually fluorescence. So the image is of a very, very high resolution down to the atomic scale. So the discovery took place in NIST, in particular, specifically on April 8th. Professor Shechtman was doing a characterization of different alloys of aluminium with a different percentage of manganese. And when he actually reached 25% of manganese, he saw the following diffraction pattern, which it's noted quite nicely in his notebook, that he was very surprised to see this sort of diffraction pattern. He never saw this sort of diffraction pattern before, and he wanted to look for explanations for this kind of diffraction pattern. And the most probable explanation for this would be crystal twinning. So he wanted to verify that what he observes is actually crystal twinning. And in order to do that, he wanted to do a set of experiments finding these twins. So the first thing he did was a micro diffraction. in which basically you converge a very thin beam on the sample, in this case 20 nanometers beam. And the point is that since the beam is so small, you never hit the borders of the crystals, meaning you only hit the crystal, it's the single crystals, and not you never hit the boundaries as noted here in this figure. He got the following diffraction pattern, meaning he never saw actually any evidence for twins in this macro diffraction, and continued the macro diffraction on different parts of the crystals, and that's the only diffraction pattern that he got. So this theoretically also could mean that the twin crystals are actually smaller than 20 nanometers, but this is very improbable, and again, since he did it on different parts of the crystal, then it's practically impossible. In addition, he also did the X-ray diffraction, in which he did not note any twins, and he also did the dark field measurement, which is basically the idea is that the light that goes to the microscope is the scattered light and not the reflected or transmitted, and therefore we get the very dark image. And again, he did not manage to observe any indication for twins. At this point, he was quite convinced that he found something new, and he continued to investigate and build a model for this discovery. So basically, what you observed was not we found out that what you observed was did not have a tenfold symmetry, but it actually had a twofold symmetry 15 times, a threefold symmetry 10 times, and a fivefold symmetry 6 times. So again, he had a fivefold symmetry, which is a forbidden symmetry, not the tenfold as he thought at the beginning, but a fivefold. And therefore, with these kinds of symmetries, the name of the symmetry is called the icosahedral, often also called the icosahedral phase, and actually many quasicrystals are of this phase. And the name of icosahedral is somewhat intimidating, often maybe. I think most of us actually kind of miss it in this time with the virus. So how exactly can we understand quasicrystals? I think the best way would be first to generate them and then reflect and analyze each step that we did. So the first thing would be is I would first use the method that is called the cut and project method. So in this method, we take a certain dimensional plane, in this case, of course, a two-dimensional plane, and that is symmetric. That's important. And on this plane, we draw a line that has a certain degree alpha, which must satisfy this constraint that the cosinus over the sinus is equal to the golden ratio tau. And it's important to note that the line that we draw never crosses a lattice point. We draw boundaries, and from the lattice points within those boundaries, we project onto our line. And notice that we get here basically a tiling, just one-dimensional tiling, or segments, but the best would be to call it tilings, I think, of long and short tilings. So the tilings here are actually aperiodic, and basically the idea is that we come from a higher dimensional space of a symmetric lattice, in this case 2D, and we project onto, as I said, a plane, a line that has an irrational slope in a lower dimensional space, in this case 1D, because it's only a line. And indeed, they found that with the models that the icosahedral symmetry is not symmetrical in 3D because it's quasi-periodic, it's aperiodic. That's the whole point of the crystals, but it is periodic in a higher dimensional space. In that case, a 6-dimensional hyperspace, basically. So that's very interesting, I think. And we can see here that the ratio between the long and the short tilings is again the golden ratio, the limit of the Fibonacci sequence. The golden ratio comes quite often with the ratio between sizes of the diffraction patterns. The ratio between those diffractions is often just the multiplicity of tau, or could be tau squared, etc. So the golden ratio here comes quite often. As I said before, the discovery was in April 82, but we can actually see that the first paper was published only in November 84, so actually 2.5 years later. The reason for this was the disbelief and the skepticism from the scientific community. Shechtman was even later removed from his research group in Israel, since he insisted on investigating and continue his research on quasi-periodic crystals. And indeed, the most notable criticism came from chemist Linus Pauling, a two times Nobel laureate, once for chemistry and once for peace. He is considered often as the most important chemist in the 20th century, and he argued that what Shechtman observed was indeed crystal twinnings. He even suggested several models explaining this observation, but all of his models were actually rejected by the scientific community. Nevertheless, he was quite sure of himself that, according to many interviews of Shechtman, during a conference in the United States, Pauling said the following quote, that there are no quasi-crystals, only quasi-scientists. So it took some time, but at the end, the scientific community accepted the Shechtman's discovery, of course with verifications of many other research groups that found also quasi-crystals with different phases. And as you can see, the definition of a quasi-crystal actually changed from what we saw before to any solid having essentially this discrete diffraction diagram, and aperiodic crystal is any crystal in which 3-dimensional lattice periodicity can be considered to be absent. And we can see that it took some time until the official definition was changed, and this happened only in 1992. So few of the properties of quasicrystals, they often show relatively similar properties as glass. They're brittle, meaning they do not deform that much under stress, but they break. They have low electrical and thermal conductivity. They are corrosion resistant, and they have a low friction coefficient. So actually, some of the applications are that well, in Sweden, a company managed actually to create quite a very highly resilient steel, and when they wanted to analyze the atomic structure of this steel, they found that one of the phases this steel has is actually of a quasi-crystal embedded inside. The other applications are especially in the coatings, for example, heat insulation or conversion of heat into electricity, and also quite a useful property is the low adhesion quasicrystals have, and they can be used as a surface coating for frying pans, since the meat does not stick that much to them, and they do not get scratched that easily as a Teflon, so they can potentially replace Teflon. They're also used. They can also be used as catalysts. A group from Japan actually managed to find quasicrystals that might be that are useful and cost-effective for the production of methanol compared to the traditional catalysts, and they can also be used in photonics actually. So these are the references that I used. And thank you very much for your attention, and I'm looking forward to your comments and questions. Thank you.